Good morning, girls. Today we are going to see paths and circuits in graphs. In the previous class, we seen graph definition, etc. Now today we are going to see about paths and circuit. So before that, today content is isomorphism, subgraphs, and edge disjoint subgraphs, and a puzzle with multicolored cubes. And walk, paths and circuits. So today we are going to see these content, and connecting this we get the connected graph and disconnected graph definitions. Okay. Now what is isomorphism? The graph G and G dash are said to be isomorphic to each other if there is a one-to-one correspondence between their vertices and between their edges, such that the instance relationship is preserved. Okay, there is a one-to-one correspondence between vertices and edges. Isomorphism means what? There is a one-to-one correspondence between edges and vertices. Okay, so isomorphism graphs must have same points. First one, same number of vertices. Isomorphism graph must have same number of vertices, same number of edges, and an equal number of vertices with a given degree. Okay, see that these are isomorphic graphs with 8 vertices. Isomorphic graphs with 8 vertices. Next, another example for isomorphic graphs. These are the isomorphic graphs. See the vertices and edges. Okay. Next term, not isomorphic graphs. So see that these three are non-isomorphic. Why? In A and B, vertex X and Y are having same degree 3. In A, there are two pendant vertices, U and V, adjacent to X. But in B, there is only one pendant vertex, W, adjacent to Y. Okay. Again, see that two graphs, non-isomorphic graphs. There are two pendant vertices, U and V, adjacent to X in A. But in B, there is only one pendant vertex, W, adjacent to Y. So these two are non-isomorphic graphs. Okay. Next, subgraphs. What is meant by subgraph? A graph G is said to be subgraph of G if all the vertices and all the edges of small g are in capital G. And each edge of small g has the same end vertices. Each edge of G, small g, has the same end vertices in small g as in capital G. Okay, again, what is the subgraph? All the vertices in small g are in capital G itself. Then the graph G is said to be, small g is said to be subgraph when all the vertices in small g are in capital G and each edge of small g has the same end vertices in small g as in capital G. Then small g is said to be subgraph of capital G. Okay. Next term, see the example graph. Graph and its subgraphs are given here. See that. Can you catch all the vertices in small g are in capital G, and vertex in small g has the same end vertex. Edge in G, small g, has the same end vertex in capital G as in capital G. Okay. Graph and its subgraph. Okay. Next, edge disjoint subgraphs. From the name itself, the subgraphs are distinct. Edge disjoint subgraphs. The edges are distinct in the subgraphs. Okay. Next, we have interesting puzzle with 4 colored cubes. So what is 4 colored cubes puzzle? Read the problem. We are given 4 cubes. The 6 faces of every cube are variously colored, blue, green, red or white. Is it possible to stack the cubes one on top of the another to form such that no color appears twice. No color appears twice on any of 4 sides of this column. Can you catch the problem? There are 4 cubes given. 6 faces of every cube are variously colored. By color, blue, green, red, white. What is our question? Is it possible to stack the cubes one on top of another to form such that no color appears twice in any of 4 sides of the column? Okay. Is it possible? Do the find the solution in the picture. Step 1. Draw a graph with 4 vertices B, G, R and W, 1 for each color. Pick a cube and call it cube 1. Then present its 3 pairs of opposite faces by 3 edges drawn between the vertices with appropriate colors. In other words, what we did means, if a blue face in cube 1 has a white face opposite to it, draw an edge between B and W in the graph. Okay. See the figure. Cube 1, cube 2, cube 1, cube 2, cube 3, cube 4, like the colors, 4 colors are like here. Okay, 4 colors are like that. We have to draw the edge between the vertices. So, do the same for the remaining 2 pairs of faces in cube 1. Put label 1 on all 3 edges resulting from cube 1. A self loop with edge labeled 1 at vertex capital R. For instance, cube 1 had a pair of opposite faces, both colored. Repeat the procedure for the other 3 cubes one by one on the same graph until we have a graph with 4 vertices and 12 edges. 4 vertices and 12 edges. See the graph, we arrived the steps like, after the final steps we can get the graph like. Okay. Next, the 4 cubes are presented together and corresponding graph is given in the side. So, see that we can possible to arrange the 24 sides. Finally, we get the degree of each vertex is the total number of faces with the corresponding color. For the cube, 5 blue faces, 6 green faces, 7 red and 6 white. Okay, totally 24 we obtained. Okay, next. Again, we have some conclusions from this. 2 opposite vertical sides of the descent column of 4 cubes, say facing north and south. A subgraph with 4 edges will represent these 8 faces, 4 facing south and 4 north. Each of the 4 edges in this subgraph will have a different label 1, 2, 3 and 4. Moreover, no color occurs twice. No color occurs twice on either the north side or south side of the column, if only if every vertex in this subgraph is of degree 2. Okay. Exactly the same argument applies to the other 2 sides, east and west of the column. Thus, the 4 cubes can be arranged if only if there exist 2 edge disjoint subgraphs, each with 4 edges, each of the edges labeled differently and such that each vertex is of degree 2. So, for the set of cubes already shown in the figure, this condition is satisfied. The 2 subgraphs are shown in already figure 2. So, go back. These are the graphs. 2 edge disjoint subgraphs of graphs for 4 cubes. We obtain this east-west subgraph, north-south subgraph. We can get the subgraph like. Okay. Important terms: walk, paths and circuits. walk, path and circuit. So what is walk? A walk is defined as it is a finite alternating sequence of vertices and edges. Finite alternating sequence of vertices and edges, beginning and ending with vertices, such that each edge is incident with vertices preceding and following it. No edge appears more than once in the walk. So see the graph. Here there is an open walk is given. Open walk is given. So no edge appears more than once in a walk. No edge appears more than once in a walk. So starting from V1, V2, in between the edge is A. So V1, A, V2, F, V3, H, V4, E, V2, B, V3, C, V3, D, V4. Okay, no edge appears more than once in an open walk. Okay, next. See that walk is given like V1, A, V2, B, V3, C, V3, D, V4, E, V2, F, V5. No edge repeated. No edge repeated. So no edge appears more than once. So without repeated of edge, we can write the open walk. Okay. Next. Path. Path of length 3 is given here. A walk may begin and end with the same vertex, such that closed walk. Such a walk is known as closed walk. A walk may begin and end with the same vertex means it is what? Closed walk. Otherwise it is open walk. So an open walk in which no vertex appears more than once is called a path. So what is path? Open walk in which no vertex appears more than once is called a path. So see the figure. V1, A, V2, B, V3, D, V4. Okay. V1, A, V2, B, V3, D, V4. It is a path of length 3. So in this we have only 3 edges. A, B, D. 3 edges. A, B, D. Okay. Next we have circuit. What is meant by circuit? So from the name itself we can guess it is a circuit. So a closed walk in which no vertex, except the initial and final vertex appears more than once is called a circuit. We start and comes round and end with the same vertex. So closed walk in which no vertex appears more than once is called a circuit. So in the given 3 different circuits are given. Okay. Next, connected graph. What is meant by connected graph? From the name itself we can guess connected graph. A graph G is said to be connected if every vertex can be reached from any other vertex. Every vertex can be reached from any other vertex. That is connected graph. So if there is at least one path between every pair of vertices in G, connected graph means there exists at least one path between every pair of vertices in G. So here graph with the 3 vertices and 4 vertices are given. So see that all are connected. We can come to one vertex from any other vertex. Okay, connected graph. Next, a disconnected graph with 2 components. See that 2 graphs are given, they are disconnected graph. Okay. Next, disconnected graph with 2 components. See that they are disconnected. There is no connection between these 2 components. Okay. So next important theorem, a simple graph with n vertices with k components. A simple graph with n vertices with k components can have at most how many edges? How many edges? N minus k into n minus k plus 1 divided by 2 edges. So, a simple graph with n vertices with k components can have at most n minus k into n minus k plus 1 by 2 edges. This is a theorem statement. Now prove. Let us assume that the number of vertices in each of the k component of a graph G be n1, n2, etc., nk. Then, which implies what? Sum of the components equal to n. n1 plus n2 plus etc. nk equal to k. Nk equal to what? N. Given that n vertices. Graph with n vertices. So, adding all these k components, we get n. So, n1 plus n2 plus etc. plus nk equal to n, where ni is greater than or equal to 1. Next, what is the maximum number of edges in a simple graph with n vertices? So, the maximum number of edges in a simple graph with n vertices is n into n minus 1 by 2. It is a standard result, already we proved. So, take that the maximum number of edges in a simple graph with n vertices is n into n minus 1 by 2. Therefore, the maximum number of edges in the ith component of G. Maximum number of edges in the ith component of G is given by ni into ni minus 1 divided by 2. Ni into ni minus 1 divided by 2. Ith component. So, adding all this, come to G. Hence, in G, we have half into summation I equal to 1 to k ni into ni minus 1, that is equal to half into summation 1 to k ni square minus half into summation 1 to k ni, which is less than or equal to half into n squared minus k minus 1 into 2n minus k minus n by 2. How we arrive this result? It is given here. We know that summation I equal to 1 to k, ni minus 1 equal to what? N minus k. Squaring on both sides, we get the derivation and obtain the result. Summation 1 to k ni squared equal to n squared minus of n minus k into 2n minus k. So, substituting this result and simplifying, we get what? Half into n minus k into n minus k plus 1 number of edges in G. The result is proved. Okay. The graph with n vertices and k components can at most have how many number of edges? N minus k into n minus k plus 1 by 2 edges. Okay. Very important theorem. Next, we see the Euler graph and Hamiltonian paths. Euler graph and Hamiltonian paths. Very important graph, Euler graph and Hamiltonian paths. So, in this, we may see that Euler line, Euler graph, and necessary and sufficient condition for a graph to be Euler graph, and application of Euler graph, and unicursal line and unicursal graph. We are going to see these content. So, what is the Euler graph? A closed walk which contains all edges. A closed walk which contains all the edges of a graph is known as Euler line, and the graph is known as Euler graph. Okay, here two examples are given. Star of David is the most important example. Star of David. See that closed walk which contains all the edges of a graph is which contains all the edges of the graph. So, Euler graph is known as Euler graph. Star of David. Okay. Next, see that how it is known as star of Euler graph. Start from V. See the figure. 12 vertices and 18 edges in this. So, if you start from V, I put arrow here, see the arrow. So, green parts and come to V and go along red path. Go along red path and reach V. So, all the vertices are covered. So 12 vertices, 18 edges. Okay, start from V along green path, complete the green path and come to V and start the red arrow and travel the red line and come to V. Okay, so Euler graph. What is mean by Euler graph? What is meant by Euler graph? A closed walk which contains all vertices of G. So closed walk which contains all vertices of G. That means a sequence of vertices and edges starting from vertex, go along edge, vertex, and return back to the starting vertex. Closed walk. Okay, without repeating any. It's a Euler graph. Very important Euler graph. See the graph and path here. 12 vertices, 18 edges of Star of David. It's an Euler graph. Okay. Next, it is like a small game you may play it in your younger age. That is continuous line without retracing and without lifting the pencil from the paper. We are all played in our younger age. Draw a line without retracing and without lifting the pencil from the paper. The resulting is our Euler graph. Isn't it? Okay, very interesting graph, Euler graph. Next, unicursal graph. What is meant by unicursal graph? Again, it is an open walk which includes all the edges of a graph without retracing any edge. Open walk includes all the edges without retracing any edges. Unicursal line or open Euler line, and graph is called as unicursal graph. Okay. Next, the walk. See that in the graph, unicursal graph, the walk A, starting from A, 1, C, 2, D, 3, A, 4, B, 5, D, 6, E, 7, B. 7B. Note that here we start with the start with the vertex A, but end with the vertex B. Open walk only. This is an open walk in which no edge is repeated. No edge is repeated. So A1C, 2D, 3A, 4B, 5D, 6E, 7B. Vertex may be repeated, but no edge repeated. It's an open walk and is known as unicursal graph. Okay. Next, one important theorem. A given connected graph capital G is an Euler graph if and only if all vertices of G are of what? Even degree. All vertices of G are of what? Even degree. So see that graph with the 4 vertices is given. Here V1, V2, V3 are all degree 2. So simple graph taken. Now in theory part, suppose we take G is Euler graph. Therefore G contains what? Euler line. In tracing this Euler line means a closed walk. So in tracing this closed walk, every time the walk meets a vertex V, it goes through 2 new edges instant on V with one entered and other exited. One entered and other exited. Okay. So see the path V1A, V2, B, V3, C, D, 4, C, V4, D, V1. Here degree of vertices is 2. Thus, if G is Euler, the degree of every vertex is what? even. Here only simple 2, degree 2. So it is a even degree. Okay. Next, converse part. Assume that all the vertices are of even degree. We have to prove what? It is a Euler graph. So for that, construct a walk starting at an arbitrary vertex V and going through the edges of G such that no edges is traced more than once, tracing as far as possible. Since every vertex is of even degree, we can exit from every vertex we enter. The tracing cannot stop at any vertex but at V. And since V is also of even degree, reach V when the tracing comes to an end. Okay. In this closed walk H includes all the edges of G. Capital G is an Euler graph. Okay. Conversely also proved. So Euler graph means if and only if every vertex of degree is what? Even. Okay. Very important theorem. Very good. Next. Otherwise, if not means what we arrive the conclusion. Remove from G all the edges in small h and obtain the subgraph h dash of G formed by the remaining edges. Since suppose G and capital G and H have all their vertices of even degree, the degrees of the vertices of H dash are also even. Okay, see the graph, then it is clear to you. Moreover, H dash must touch H at least at one vertex because G is connected. Okay, so starting from A, again construct a new walk in graph H dash. Okay, so here H dash and A are given. See the graph and do the process. We get, okay, again we get the degree of every vertex is what? Even. Next term, another important term, Hamiltonian circuit. Hamiltonian circuit. So, what is meant by Hamiltonian circuit? See the figure. The dark lines are, dark edges, dark lines are gives your concept. Start from V and goes through the arrow edges and come to V. So, it travels all the vertices. The path contains all the vertices of G. So, the circuit contains all the vertices of G. Okay. Next, Hamiltonian circuit definition. A Hamiltonian circuit is a connected graph. We define in a connected graph, it is a closed walk that traverses every vertex of G exactly once. Every vertex of G exactly once, except the starting and end vertex. So, Hamiltonian circuit in a connected graph defined as, it is a closed walk that traverses every vertex of G exactly once. Every vertex of G exactly once. Okay. Next, example, complete graph. From this, another concept will come, going to another concept, complete graph. What is complete graph? A simple graph in which there exists an edge between every pair of vertices. Edge between every pair of vertices is called complete graph. See the example, two vertices, there is an edge between two vertex. So, it is a complete graph. Again, three vertices. In three vertices, all the vertices are connected. So, we have a edge between every pair of vertices. So, it is a complete graph with three vertices. Next, complete graph with four vertices. Complete graph with four vertices. Okay. Next, complete graph with five vertices. Okay, complete graph. Example, universal graph. Another name, click, or universal graph. Complete graph, another name is what? Universal graph or click. So here example with complete graph with the 2 vertices, 3 vertices, 4 vertices and 5 vertices are given. Okay. Next, remaining we see tomorrow. Okay.